Hi, this is Dr. S and welcome to video 8 of my series on aromatic chemistry for OCR A-level. At the end of my last video, I asked you to practice your mechanism skills by trying to draw the mechanism for the reaction of methylbenzene with bromine to form 4-bromomethylbenzene and HBr. Now what we should have found is that the Br2 is not an electrophile that can react with the benzene. We have to produce a reactive electrophile in order for the bromine to go onto the benzene. And we do that by taking my bromine and reacting it with a halogen carrier, such as FeBr3, to form FeBr4- and a Br plus ion, which is a strong electrophile. That can then approach my methylbenzene, and a movement of a pair of electrons can occur from the pi system, the circle, to the Br plus ion. That then creates the intermediate. Now you have to be careful with this intermediate because it already has a methyl group on. So the methyl group I'm still going to put at the top of my benzene ring. I'm trying to make 4-bromomethylbenzene, so the substitution position has to be opposite the methyl. So that's this position here. So that is where my bromine is going to attach to the ring. That makes this carbon here the one with 4 bonds and the one that cannot take part in the delocalization. So my horseshoe shape opens up towards that side with my positive charge in it. Now the electrons from the carbon to hydrogen bond can move back into the ring in order to regenerate the delocalized system. We have a methyl on the top and a bromine on the bottom. That produces an H+, and then the H+ can then react with the FeBr4- generated here to remake my halogen carrier, therefore making it a catalyst and producing HBr. Okay, now this is the bit that's going to cause problems for people, the intermediate. Some people like to have the substitution position at the top all the time. If you do that, you've got to rotate the entire molecule. So an equally acceptable intermediate here, I'll just do it up here, where the substitution position is on the top. So my H and my Br is there, but I've got to imagine this being rotated around. So the methyl is now on the bottom. You've got to be really careful with your positioning of these. Okay, in this video I'd like to concentrate on the nitration of benzene. So this is the reaction for the nitration of benzene. The reaction of benzene with nitric acid to produce nitrobenzene and a water. Now again, the nitric acid is not something that will react with the benzene on its own. So we need to generate a strong electrophile. I do that by mixing concentrated nitric acid with concentrated sulfuric acid. Two very concentrated acids, not a particularly nice reaction mixture, that. And that will form this ion, and a water. It's the NO2 plus ion, or what we call the nitronium ion. That is the strong electrophile. So that's going to be the thing that then approaches my benzene, and a movement of a pair of electrons can occur from the ring, just as in the previous mechanisms. That then produces my intermediate. So just the same with the bromine, we have a substitution position. We'll do this on the top where the NO2 goes on. That's a carbon with 4 bonds, so it cannot take part in the delocalized system, so there's a positive charge and a horseshoe that way. Movement of a pair of electrons down from that bond to there, and then that produces my nitrobenzene and an H+. That H+ can then react with the HSO4 from up here, the HSO4- to regenerate my sulfuric acid catalyst. So it shows that that is being regenerated. That's a catalyst. So your overall reaction is benzene plus nitric acid makes nitrobenzene and water. Okay, I hope that's clear. Now, the nitration of benzene can be quite a difficult one to control. Okay, most nitration mixtures in general organic chemistry involve concentrated acids here, nitric acid, sulfuric acid. They can be very reactive and quite dangerous, so most nitration mixtures take place at temperatures below 10 degrees to prevent the reaction getting out of hand. If you do some further research, you'll also find that a lot of explosives have nitro groups in. So it's a safety mechanism. Now actually, because this reaction is not that reactive, it needs to be a little warmer than that. So we carry out this reaction at 50 degrees C. But you have to really carefully control that temperature, because nitrobenzenes can be susceptible to multi-substitution. So I might not only put a nitro group here, I might also put a nitro group somewhere else on the ring. And if I do that, I'll have a complicated mixture of products. If the reaction occurs above, say, 70 degrees, you'll probably get more than one nitro group on there. So it has to be very carefully temperature controlled at 50 degrees C. Okay. In my next video, what we'll look at is how to add alkyl groups onto benzene rings. So rather than making a bond between a carbon and a nitrogen, or a carbon and a bromine, I'll be making bonds between carbons and carbons, and that's a really important technique in organic chemistry. I look forward to doing that. Okay, I'll see you then.